Okay, as we all know, when we have y to the first power times y to the second power, of course, you just add the powers together and you end up with y to the third power. But have you ever thought about, what if we have y with 1 prime times y with 2 primes? What are we going to get? Oh well, the answer is y with triple primes, with 3 of them. And of course, you guys know, this right here is not true, in the sense that this right here is not true for all functions, but this right here is true for some functions. For example, if y is a constant function, then of course, its first, second, and third derivatives, they are just 0, and you end up with 0 is equal to 0. That is true, but it's also boring. So in this video, we are going to do some math for fun. We are going to find out some non-zero and non-trivial functions so that its first derivative times its second derivative will be its third derivative. So that's what I want to show you guys in this video. However, look at this right here. We have a third order differential equation, which is pretty bizarre. And you can actually reduce this by saying let another letter, let's say phi or whatever that you want. You can say phi is equal to y prime. And then you can just change that to phi times phi prime equals phi double prime from here to here with this substitution. This is good, but the problem is that we like to work with x and y. If you take this approach, it's going to be really confusing with all the letters later on, so I'm not going to do that. Instead, I'm going to show you guys this. My goal is first to find y as a function of x, like this. Again, y as a function of x. This is just my notation for that. And I'm going to assume that y is invertible. It has an inverse. That's going to be important later on. I'm going to find a y as a function of x such that y times y prime equals y double prime. And this is really similar to the phi times phi prime is equal to phi double prime. But again, we like to work with y and x. And of course, I'll do this for you guys first. In the end, just integrate the answer right here and we can get that. Same thing, right? So we'll focus on this. And again, this equation is in green and red, Christmas color. This equation is in black, so they are technically different. Anyway, enough talking. Let's see. Second order, we don't like. We don't like it. Let's reduce the order. Let me begin by doing a substitution. So here we go. I will say let, and just pick a letter that you like. Let me just use u. Why not? Not the u substitution. Okay, we're doing differential equation. It's more high tech, right? Let u being y prime. So as you can see, then from here, this right here is the u. That's good. And y double prime is just like you differentiate both sides, you get u prime from here to here. That's good. But the problem is that, okay, this is that. What's y then? If u is equal to y prime, if you integrate both sides, sure, y is the integral of u, but the problem is that I don't think you want to put an integral in your differential equation. That's a horrible idea. So in fact, I'm just going to keep y as how it is, like that. Therefore, with this substitution, we have the equation now being y times u equals u prime from here to here. So this looks pretty good, but let's see what we can do. First of all, let me show you what not to do. Some people may want to just divide both sides by u, and let me write it down. And you look at this as y equal u prime over u. And some people may recognize this as the derivative with respect to x, natural log of u, like that. Because if you differentiate natural log of u, you put the u in the denominator and use the chain rule, you multiply by u prime on the top. So this is the same as that, and you still have the y. And some people may want to get rid of the derivative by integrating. Sure, this and that will be cancelled, but remember, you are integrating with respect to x on both sides. The trouble is, you don't know what this is. You cannot integrate y with respect to x without knowing what y is. Don't do that. So, Ah, my God. This is how we are going to continue though. We will actually have to look at this equation, and we will have to look at y as our new independent variable, and then u being our new dependent variable. So what do I mean? This is like your new x, and this is like your new y. That's pretty much the idea. And to make things clear, in fact, we will actually have to use more substitution. Just deal with this, you're in differential equation, so you should be able to handle it. Again, y is our new independent variable, so I'm going to call the new function to be w, and the input will be y. So this is the new function, with y being the input. Well, what's the choice of w then? I'm not going to let this equal to u prime whatsoever. Instead, I'm going to look at the u, and the input is going to be the following. This is kind of strange, but pay attention to this. You can do it too. Again, let's come back to here. Y as a function of x, and I said it, y is assumed to be invertible, meaning it has its inverse. So if you write y as a function of x like this, well, if you write it backwards, x of y, this right here, you are saying the inverse of this function. And look at the y is the input. Enter that into the x function, and then enter that into the u function. So both sides, they are in terms of y. Let me give you guys a quick example. Suppose you have y as a function of x being square root of x. X is your input. And of course, in this case, x has to be greater than 0. And let's say this right here is your original. Well, its inverse, as we wrote it down over there, we wrote it as x of y. Right, so that's the inverse. And of course, the inverse of the square root is just the square function, but the input here is the y. So you have y squared like this. And of course, in order for this to be true, well, technically greater than or equal to, but this is the idea. So now, both sides, they are in terms of y. So what we are going to do next is that look at the right hand side. Again, we are treating this as a new equation with y being the independent variable. I want to look at this now and differentiate both sides with respect to y. And to do so, let me just put on d, dy, d, dy on both sides. Therefore, on the left hand side, we end up with dw dy. Well, for this right here, look at this. You have u of x of y, so you have to use the chain rule.
Use the chain rule!
And the best chain rule is going to be the following. I'm going to put on du over dx first, and then times dx, dy, like that. Well, in fact, you know what these are, but you have to change it a little bit. Let me show you. On the left-hand side, I'll write down dw over dy. I will keep this on the top, du dx. You know what this is, right? I'm going to take this down. Well, technically, you have to flip that, and you end up with dy dx. You take this, I take this part, and you have this now in the denominator. And now, let's take a look. So what is dw dy then? Well, du dx is precisely our u prime. Now, when you use the prime notation, you have to remember we are differentiating this with respect to x. So this right here, I can write it down as u prime. So that's good. So we have u prime on the top over. And similarly, when you have dy dx, you can just use the prime notation to keep track. And that's precisely our y prime, like that. Again, dw over dy, like this, is u prime over y prime, like this. And again, you started from the chain rule, and then you get that. So that's cool, huh? Very nice. And yeah, so hopefully so far so good. And we know u prime is that. Look, we know u prime is this. So I'm going to put y times u into here. So in another word, we get y, which is in black, I'll just put it down in black, why not, times u over, and do we know what y prime is? Look back right here, and y prime is just the same as u, so that's wonderful, isn't it? So I will just, let's see, I will write it down in blue. Why not? I'll box this in blue, and then I'll put this down in blue. Again, y prime is the same as u, so we have that. So what's this? Cancel, cancel. You get just a y. This is wonderful, and we will continue. So let me just write it down right here for you guys. dw dy is equal to y. And now we have a more legitimate differential equation to solve. We can just multiply both sides by dy, and then we end up as dw equals y dy, and then we are going to integrate both sides. On the left-hand side, we just have w. Technically, you put plus c, but it doesn't matter because you can just put a plus c on the right-hand side. This is technically plus c1, and this is plus c2, and then you can subtract the constants. You just have a constant on the other side. So you have w here, and then this is equal to integrating this with respect to y. This is legit, okay? And of course, you end up with 1/2 y squared plus our first little constant. I will write it down as c1 like this. Very good. And of course, w is still a function of y. So you see, this is still true, isn't it? Very nice. And now for w of y, of course, we can look back to here. W of y is the same as that, so we can write down u of x of y for w of y, and that's equal to, of course, still 1/2 y squared plus c1. And for this right here, for the u, we can look back to this. And of course, this right here is just y prime. So I'll write this down right here for you guys, y prime. And that's equal to 1/2 y squared plus c1. And we finally have a differential equation that we know how to solve because y prime is just dy dx. Remember, we have been using the prime notation for the derivative of something with respect to x. So this, I will actually use back now. This is dy dx. And then of course, the right-hand side is this. But this is a separable differential equation. And let me just factor out the 1/2 because it's easier this way. I will keep it as y squared. And I factor out 1/2 from c1. Technically, I should put down plus 2c1. But it's just a constant anyway. So I just put down plus c2 like this. And let me divide this on both sides. And let me multiply dx on both sides. I will keep the 1/2 here. So I end up with 1 over y squared plus c2, and then the dy here, and that's equal to 1/2 dx. And this is so wonderful. And here's the deal. Yes, we can integrate this, but there are 3 cases. It depending on what kind of value that we have for c2. Well, we have to consider if c2 is 0, and the second situation if c2 is less than 0, and the third situation is when c2 is greater than 0. So just imagine if you have to integrate 1 over y squared. Well, you have to do the reverse power rule. If you have, let's say, c2 being -1, well, you might want to do partial fraction or use the inverse hyperbolic tangent. And if c2 is positive number such as +1, then you just get the inverse regular tangent. Well, I'm not going to show you guys all 3 cases because I just want to find a function for you guys. So I will just make a note right here for you guys. I'll just put I will do when c2 is greater than 0, and I'll pick c2 is equal to 1. So I will continue right here. And we have 1 over y squared plus 1, all right? Okay, we're almost done, trust me. And then we have the dy, and that's equal to 1/2 dx. And then, of course, integrate both sides. On the left-hand side, this is why I picked just 1, because we get the inverse tangent, and this right here is y. And you don't need to worry about the plus constant, just put it down on the right-hand side. This is equal to 1/2 x, and then plus, because as you see 2 over there already, let's say c3, like that. And then, of course, we can just apply the original tangent on both sides. So in another word, we get y equals the original tangent of this being inside. 1/2 x plus this right here is going to give us c3, of course, like that. You take the inverse on both sides, like that. And this is so wonderful. And yeah, very cool, isn't it? However, though, this right here, as I said, it will only satisfy this. So I will actually go back to the green marker for you guys. And here is the deal. And let me just write this down again for you guys. If you want to satisfy y prime times y double prime being equal to y triple prime, all we have to do is integrate this result. Because again, this right here satisfies this. And the connection between this and that is just integrate this answer. And that'll be it. So I will just put this down right here for you guys. Y is equal to the integral of this. I will just put down tangent of 1/2 x. And for simplicity purpose, let me just say C3 is equal to 0. So I'll just say pick or choose whatever you want to use. C3 equal 0. And that's pretty easy right here, of course. You can pick whatever C3 you want, of course. And we're integrating this with respect to x. And again, earlier you could have let C2 being 0, and that would be pretty easy as well. But if you pick C2 to be 1, you end up with tangent. I think it's more interesting. Anyway, when you integrate tangent, of course, you end up natural log, absolute value of secant, and then the input is still the same, 1/2 x. And notice that the derivative of 1/2 x is just 1/2, and the chain rule says you have to divide it by the derivative inside because you're doing the antiderivative. So the derivative of 1/2 x is just 1/2. When you divide it by that, you have to multiply by a 2 right here. So here is your y. And again, you integrate it, so technically you should put down plus C4. Yeah, and the truth is, look, you started with the third order differential equation. And you have, technically this right here, use first constant because I kind of factor it. You didn't have to do that. But you have 1 if you keep it, 2 if you keep it, 3 if you keep it. You have 3 arbitrary constants. You technically have to keep them for the final answer in the general form. But for simplicity purpose, I will just say I will pick C4 to be 0, just to be easy. So I will tell you guys, this right here is a function that will satisfy this prime addition addiction. Really cool. I will convince you guys real quick. So this right here, let me just do it for you guys. If you look at this and differentiate, guess what? You'll just get that back. That's why integral for that. And then you end up with tangent of 1/2 x. Very good. And then when you differentiate this again, you get the y double prime. Well, you end up with 1/2 because of the chain rule from here, and then you end up with the secant square of 1/2 x, like that. And if you do the usual technique to differentiate this again, y triple prime. Let me tell you, you bring the 2 to the front and you get 2 times 1/2 is just 1. But later on, you are going to end up with the chain rule again, right? So you still have the 1/2. And then the derivative of secant square, it's going to be secant, well, it's technically secant to the first now after you bring the power to the front, but multiplied by the derivative secant, which is secant tangent. So you still end up with secant square. And then the input stays the same, and you also have to multiply by the tangent of the same input, like this. And again, this right here is just a Cal 1 question now. I will leave you guys this right here for you to verify. And the beauty is that, yes, if you multiply this and that, you don't get your third derivative. Look at that. Oh my God, it took me so long to do this video. How pretty is this equation, right? Anyway, this is it. If you guys like this video and if you guys want to see more, be sure you guys subscribe. Thank you guys so much. I'll see you guys soon. And as always, that's it.